Hello. It's great to be part of this event. Everybody having a good time so far? Cool. Then I can bore you a little bit with messaging protocols. I decided to speak in English because 70% of the terminology I can even translate, so it really doesn't matter that much. So I was properly introduced. So basically, what I want to talk today is a little bit about messaging protocols and some design decisions in those, and where are we today and where are we going, and how we try to support some of the use cases that we're seeing coming toward the messaging infrastructure. So some of the basic concepts. So messaging, what it is, it's basically just moving data from one system to another. It doesn't matter if it's only a couple of enterprise systems where you're moving data between, or you have some kind of, like we have recently a lot of IoT use cases where you have like tens of thousands of devices where you want to move data from those devices into some kind of a cloud infrastructure. What you have in between is some kind of messaging. And messaging protocols are important because they define everything that's needed for that communication to happen. So they define contracts between the endpoints involved in messaging, and quality of service. Can we lose data? Should we not lose data? And data formats used for that communication. It's all part of the messaging protocol. I assume most of you guys coming from Java background. So when you think messaging, you first think something about like JMS. But the trick is that JMS is really not a messaging protocol. It's a programming language API, and you program against that API and try to use some of the messaging product basically. So the downside of all this is that there's no really interoperability on the network level there. So everything is vendor specific. Even if when the protocols, network protocols, messaging protocols are open, like we use in AMQP or JBoss Hornet Queue, those are open source projects with fairly open specification of their networking protocols, but they are not interchangeable. So you can't use the same libraries and connect freely to any broker you want. You are pretty much vendor constrained in that kind of terms. So in AMQP community, to come around that, we a couple of years ago came with something that was called STOMP, shortened for simple text-oriented message protocol. And the idea was to create something it's very, very simple in terms of implementation, so that people can very quickly script their libraries in any language they want. So we can easily connect PHP, Ruby, JavaScript, Java, .NET applications over the same messaging infrastructure. So the idea was to have something like HTTP protocol, just a little bit constrained over the messaging layer. So instead of having get or put operation, you have something like subscribe or send a message and things like that. But basically, if you look at the frames of the STOMP protocol, it basically looks very similar, like what you have in HTTP. There are a couple of drawbacks to STOMP is that it never got standardized, and because of its text-based nature, it has some performance penalties involved. If any of you read anything about IoT, you came across to MQTT protocol. And here you can see how the specific area and context in which the messaging protocol is used is really influence the design of the protocol. So STOMP is all about let's be as simple as possible, text-based, so we can parse it easily and things like that. But MQTT is all about network efficiency and being able to implement clients in basically embedded hardware. So it's all about how do we create our clients in the embedded hardware, and so they can use as little as possible of network traffic, because all these devices probably will communicate over some very expensive, 3G, 4G networks, or even satellite communications. And then, we finally coming to the AMQP 1.0, which is something that I would like to spend more time talking about, and that's a standardized protocol, which is a good thing. So, meaning that if you say, my broker or my messaging infrastructure is AMQP 1.0, it should be able to connect to any AMQP 1.0 client. So there's no that kind of thing that, this is ActiveMQ, this is IBM library, this is Oracle library. It's all standard on the network level. It's a binary protocol, but it's much more richer, feature-rich than MQTT. So it provides different kind of interesting features in the protocol itself, which we'll go through now and see, how some of those features will enable us to provide the scalability of the messaging infrastructure that we will need in 5 or 10 years. So first of all, we have a QoS guarantees. That's a quality of service, and that's a typical thing mostly seen in all kind of messaging. So you can have kind of fire and forget messaging when you say, I can lose these messages, so just send it and I don't care. The other thing is, I want to send this message reliably, and I will try resending this message until I success, but there's no way to guarantee in this mode that I will do this only once. So the final consumer of the message can receive that message multiple times and be prepared for that. The third one is exactly once, and it's a little bit theoretical and philosophical question. Can we actually do this in a distributed environment? But it involves three-way acknowledgement between the producers and consumers, making sure that the single message is sent only once to the appropriate consumer. Another interesting thing that AMQP provides that other protocols don't provide is its own type system. So basically, all the headers inside of the protocol, even the message body, can be specified using its own internal type system. So you can ask, why do we want to do this? It's simple because, if you use Stomp or you use MQTT, you will end up, inventing your own type system on top of it. You will use some kind of the JSON or protobuf or something like that. With this, you have this built into the network protocol itself, and that further enables integration of multiple different environments, like going from one language to another language. You can be sure that all your primitives and lists and maps are properly encoded decoded in different environments. And this also enables us to do something else that people started doing recently, which is very interesting. That is to providing a kind of messaging API for your system. So instead of providing your customers or partners with programming language API or just pure REST protocol API, you can define your gateway into the system in terms of AMQP. So you define because we have this type system, we can nearly specify how the message is coming in and out of the system should look like, and how that message exchange should look like. So that's one of the benefits that's being used a lot lately. And the main feature of AMQP is that it's a symmetrical protocol. So every other messaging protocol that we covered so far is kind of a client-server architecture. So it implies that there's a client and there's a broker. So you send your messages via some broker inside. AMQP is designed to be symmetrical, so you can have broker and use a classical brokered messaging, but you can also have direct messaging between the clients, because those clients are equal in all terms. And you can introduce a new component which we call message router, and we will cover that topic in more detail in a couple of minutes, but it's an important thing that with AMQP 1.0 we can do that. So we can have direct messages, routed messages, or brokered messages all inside of the one system. Flow control is often an important aspect of any messaging system. So just a little bit of terminology. So what's the flow control? It's like how do we constrain flow of the messages into our system? So if we cannot accept the rate of the messages that are coming in, do we have any mechanism to stop those messages, right? So that we can tune the rate of the messages that we are actually able to accept. And in that terms, you know, all the messaging system have some kind of mechanism to deal with this. But with AMQP, we have this built into the protocol itself. And its good thing is that it's defined on the link level. And that's basically, you can see that inside of the one physical network connection, you can have multiple sessions, multiple links. So, for example, a good use case for this is that you can have basically different kind of priority links inside of your one single connection, right? So low priority messages that, you know, we can afford to lose, and they are coming in large volume, but you can also have like some kind of high priority control messages that we need to deliver to the other side at any point. So with this kind of a sophisticated flow control system, we can achieve this, and we can always say, you know, that no matter how much throughput we have on the low priority links, that we have enough capacity on our connection to send, you know, high priority messages. So what consists of the, you know, AMQP messaging stacks? Basically, we have clients, we have brokers, and we have a message router. For the clients, most of those are today developed as part of the Apache Cupid project. And we have their clients for almost all you know, popular developer platforms today. You can see there that, you know, we have a Java JMS 1.1 client there, and JMS 2.0 client developed there. So you can see that, you know, the difference, that, you know, the JMS is messaging API for Java, and underlying networking protocol in this case will be used, AMQP will be used for that. On the broker side, there's a lot of work going on in ActiveMQ community in the last couple of years. There's a new sub-project called ActiveMQ Artemis, and it's basically a donation of the JBoss HornetQ project to the ActiveMQ community. And the whole idea about donating the code and going forward into a single community is to, you know, merge the efforts and create, instead of having two competing projects, have one, you know, one community and one project that will try to create an, you know, excellent broker for the next generation. And Artemis has a lot of good things about it. So it's all internal core is reactive and very scalable, and you also have a very efficient message store and message journal. So the idea is, you know, it will be a good AMQP broker, but it will also provide support for, you know, core and OpenWire brokers, so that legacy HornetQ and ActiveMQ5 clients can connect to it without any problems. And we also have support for MQTT and STOM protocols as well. Like you would expect for any modern message broker, it's developed with high availability and scalability, you know, as a first concerns. And now we're coming to the interesting part, and something that's a little bit new in terms of thinking about messaging solutions, and that's the dispatch router. And it's part of the Apache Cupid project as a separate component, and it's written as a you know, very efficient, lightweight C implementation of the message router. So let's try to understand, you know, what's the difference between the router and the broker. And the important thing is that the router never owns the message. In the classic brokered messaging case, you have a producer, you have a consumer, but producer sends a message to the broker. Broker says, okay, I got it, you can move on. So at that point, broker owns that message. So it needs to store it somewhere if it needs to be a reliable transfer or not, but the broker owns the message at some point in the transfer. Thinking about the message router, you can think about TCP network router. Just instead of routing TCP packets, it routes AMQP messages and all the supporting commands needed to actually handle the message delivery. So that has another important thing is that routers can be deployed into a kind of a network of routers. So you can have redundant paths between different endpoints in the side of the system, and you can mix and match routers and the brokers. So the router will try to do like a typical network router. Will try to do cost-based routing. So it will try to find the shortest route from the consumer from the producer to the consumer. But in case of some kind of failure, it will find an alternative route. So in this case, you get some kind of the resiliency of the system and redundancy even without storing the messages, just by providing multiple routes and of the messages throughout the system. So what this gives us, so with message routers, you can see that the brokers are very complex piece of software, just like database. You have to have a message store. There's a lot of state and a lot of context that needs to be saved and saved reliably. So there's a message store. You need to keep track of all your consumers, or of all acknowledgements of the messages. So there's a lot of things going on. Router is a simple thing. Simple thing that it's a connection handling and the routing table, and it can scale much better than the broker in certain scenarios. Especially if you can see it as like a gateway inside of the messaging system. So I will skip this a little bit to come to the important parts. But basically, having brokers and the routers, talking the same protocol there, we have a powerful toolbox that we can use to build an infrastructure that can scale a lot, and we see the need for that scale, because instead of having like a dozen of enterprise applications that needs to talk to each other, we now seeing people trying to connect tens of thousands of devices to the messaging infrastructure, and the huge number of connections, huge number of destinations used are putting the brokers to the limits of their scale. So we can do things like we can use the routers as a gateway into the system, try to use them for all the message routing and the delivery, and then just use the brokers as a storage for the reliable messages that they need to be. So here are some of the scenarios that you can think are interesting in this kind of scenario. So, for example, let's say we have a large number of connections that broker, due to its complexity and limitations, can't accept. What we can do is provide, and you can see this box, this router box is not as a single router. It can be a router network. So those connections can be load balanced across those routers, and we can have tens of thousands of connections there, and then just a dozen of connections going inside of the system throughout the broker. And by doing that, we left the broker doing with less things to do. So it will be automatically much more scalable. What we can do also is kind of a primitive message routing, or kind of a destination concentration, in terms of that if a lot of clients have a lot of different destinations that they want to write to, but from our point, it's just a single logical destination. We can do that destination transformation also on the router layer. Interesting thing, like doing destination sharding. We have too much destinations for a single broker. How do we do, how we shard those destinations across the different brokers? Again, using a simple router maps, we can configure that gateway layer to, shard those destinations across the different physical brokers in the end. Then destination partitioning, you can also imagine this case, where you have a queue that is so big that it can't be physically handled by a single broker. Again, putting a little router in front of it, we can partition that queue over the multiple physical brokers. Then, you have systems where, you can mix and match persistence and non-persistent messages. So if you have like QoS0 is a typical term for that non-persistent messaging. So those messages really don't need to touch the broker at any point, because we can lose them. There's no way to go to the broker, store them on disk, read them from disk, and then forward them somewhere else. If the consumer is there, if everything works, we will deliver those messages directly through the router network. If something fails, we can afford to lose them. That's the contract of their job. But if we have reliable messages coming through the system, those messages using the same infrastructure goes through the broker and then goes to the appropriate clients. But with this, we can hugely, in those kind of systems, hugely reduce the message volume that's coming through the broker. So in that way, we scale the broker without introducing new brokers. So that was the crash course of what ActiveMQ is and AMQP is, and some of the features of the protocol itself that allows us to introduce a new component like a message router, and then create scalable deployments using not just one broker, or try to scale to the multiple brokers, but be more creative in how we design our messaging infrastructure. Thank you.
We are on time, so we have time for questions. 2 or 3 minutes worth of time.
Može. Pa, izvini, nisam čuo posljednji deo pitanja. Pa, znači, ovo je sve dosta sveže, što se kaže. Tako da, još uvijek je sve u razvoju. Trenutno radimo na nekim projektima koji su, da kažemo, u smislu messaging as a service, da pokušamo da napravimo neki management layer za sve ovo, kako bi mogli da sve se iskonfiguriše kako treba, zavisnosti od use case-a.
Hvala lijepo. Okay, now I can switch in English. So, but generally, this goes toward the direction how ZeroMQ works. It means that.
Yeah, but not just that. I mean, with only ZeroMQ, you just have message routing. With this.
Exactly, and this is like you have a.
If you just
library, so you can build on top of it, you can build your custom broker or whatever. But so here fundamental, and because now it looks like this router and broker are a bit redundant in a way that you could build your broker on top of router and.
Well, it's not, because the broker, it's not that simple to build. That's the problem.
No, okay, yeah, you're right. Of course.
But I mean, the point is that you don't need to use the broker when you don't need it. But for a lot of use cases, the broker is still necessary. You need transactions, you need message storage and things like that. But the thing is that, and the problem is that when you want to scale out the brokers, it's not that easy. Because there's a lot of state on each of the brokers, and they need to.
This is the problem with the brokers, because they don't scale.
Yeah, and they don't scale because they have too much state, which is necessary sometimes. But if you can, remove that state from the component like a router and do it some part of the job, it makes much more easier to scale the whole system as well.
Okay, thank you. That was my question.
Cheers.
Then I have a question.
Okay. Perfect.
Do you see any of the big players, vendors, IBM, Oracle, going this way?
Yeah, they already do. So Microsoft Azure is all AMQP1, and IBM is all AMQP1, and Red Hat is all AMQP1. So it's a big thing, and it's important to say that AMQP 1.0, the thing that we're talking about here, is nothing like, and this adds a lot of confusion. It's nothing like AMQP 0.9 or 0.10 that's used a lot in other software messaging systems like RabbitMQ. They're all going there, but they're not. It's not the same protocol. And when you start Googling, you get first your examples in those kind of systems. But we are trying to change that picture.